Hello everyone, I'm Jungi from Purdue University. In this video, I'm going to present UHDM, Unbounded Hardware Transactional Memory for Hybrid DRAM NVM Memory System. This video is a short video, so if you have any question beyond this talk, please refer to the paper or watch the full version of the video. And let's get started. With the advance of persistent memory, persistent data structure have been introduced, and they have to be consistent and durable at all times, even with concurrent update from multiple threads or unexpected crashes or power failure. So concurrent updates can be handled with HDM that detects data races at one time and restart one of conflicting accesses. And crash consistency is guaranteed by hardware logging technique that provide atomicity of NVM stores. The combination of HDM and hardware logging provide durable HDM that guarantees HCID transactions for consistent and durable data structure. This is the state-of-the-art technique to provide durable transactions with HDM, and UHDM is built on top of this. In this study, we are presenting UHDM that introduced the unboundedness and support for hybrid memory to durable HDM. First, the unboundedness is essential for application transparency. Otherwise, programmers should reason about the size of transaction they are managing, and they must provide the fallback paths in case of overflow. This renders HDM programming difficult. To satisfy this requirement, UHDM must address the challenge of detecting conflict in all memory hierarchy, including on-chip caches and off-chip DRAM and NVM. The second requirement is to allow transactions manipulate both DRAM and NVM objects while providing atomicity and durability. This requirement is driven by recent programming models pursuing hybrid data structure to accelerate persistent application and ease NVM programming. For the second challenge, UHDM designed a fast-coming protocol for transactions modifying both DRAM and NVM objects inside of transaction. So in this talk, I will briefly introduce this challenge and UHDM's approach. Let me talk about the complete detection first. So commercially available HDM, such as Intel's RPM, places uncommitted data in L1 cache only, making transactions not exceeding this boundary. Although the state-of-the-art durable HDM extends the boundary to L3, but off-chip NVMs and DRAMs are uncovered. Fortunately, the AR signatures can provide unlimited data detection range, covering the off-chip caches and off-chip memory as well. However, the signature must be updated and checked for every memory access from each core, which provide a tremendous number of false positives in the Bloom filter. The false positive unnecessarily aborts transactions and decreasing concurrency. So the key challenge here is to reduce the false positive rate. So what UHDM does is to filter out conflict happening in caches with the cache coherence protocol. The cache coherence protocol actually detects the conflict and only allows cache miss request to go to the address signature below. Since they only record cache miss request, they have much less chance to produce false positives. As a result, UHDM reduces the false positive rate to 9% from 99%. This is very important to support unbounded transactions with enough concurrency. The second challenge was to provide fast-coming protocol for DRAM and NVM transactions to optimize the common case, which is commit. Since there are two types of data UHDM is dealing with, UHDM provides different approaches to each type. So UHDM use underlogging for DRAM data and redo logging for NVM data. While DRAM data commits faster with the eagle approach, which override data in place, redo logging of NVM provides fast commit, since it plays the costly cache flush out of the critical path. And lastly, USDM provides cross consistency with the NVM redo login. So this is the end of my recap of key aspects in USDM. For the evaluation, please refer to the paper or full version of presentation. And thank you for watching this video.